So, hello everyone. In the last lecture, we stopped with the comparison of the Maxwell and the Kelvin model. We also discussed that these two models on their own cannot exhibit all the responses that we want for a viscoelastic material. While Maxwell model can do a very good job of relaxation, it cannot do an excellent job as far as predicting the creep and recovery is concerned, as can be seen here. A Kelvin model can do a decent job of predicting the creep and recovery, but it cannot predict the stress relaxation response. So, what we are now going to do is we are going to combine them two. So, we are going to see that there is a Maxwell model and there is a Kelvin model, and we are going to combine them in series, and this is one of the well known model that has been used for characterizing the response of bituminous binders, bituminous mixtures, polymer gels, blood and many other fluids that are available. And you can actually see some of the nomenclature here. So, we are going to take R1 as the spring, eta 1 as the dashpot and R2 as the spring, and eta 2 is the dashpot for the model. So, you are having 2 springs and 2 dashpots, and when this material, when this model is subjected to a creep loading of this form, we are going to see a total strain of epsilon, and you can actually see that it is epsilon 1, epsilon 2 and epsilon 3. In fact, similar to the exercise that we did earlier, without even deriving all the expressions, we can try to hypothetically sketch the response of the material. So, when we subject this particular model to this kind of loading, we are going to see that there is going to be an instantaneous elastic response which is given by this particular jump, and then after that we are going to see a response which is progressing in this particular way. This is going to be the combination of the Kelvin model as well as the isolated dashpot, and when we unload it, there is going to be an instantaneous recovery due to the same spring, and then there is going to be a delayed recovery here. Okay. So, now based on the discussion that we had in the earlier lectures, you should be able to find out whether this model shows a fluid like response. So, what we will now do is we will try and see whether we can derive the constitutive model for this. The derivation of this will become a little bit involved, and you are expected to do the required algebra and try and see whether you can get this expression 29. So, epsilon is epsilon 1 plus epsilon 2 plus epsilon 3, and here epsilon 1 is nothing but the strain in the lone spring which is given by sigma by R1. Epsilon dot 2 is sigma by eta 1. What we have done here is to write the expression for the linearly viscous damper, and what we have now written here is nothing but the expression for the Kelvin model. So, the Kelvin model is connected in series. So, we have straight away taken and written the expression for this. So, now when we play around with all these expressions, try to rearrange them, we are going to get an expression of this following form. It will be useful if you could denote this in a slightly different way. Okay. So, it is going to be some material constants here of this particular form. So, you are going to have some material parameters here given by this and some other material parameters here given by this, and similarly for the strain. So, you are going to have a second time derivative of stress here, a first time derivative of stress, similarly a second time derivative of strain and the first time derivative of strain. So, you are going to have a second order ordinary differential equation in time for stress as well as in strain. So, this solution of this equation is necessary for us to find out how the creep and recovery response is going to be as well as the stress relaxation. It is actually not very difficult to solve this problem. So, if we need, since we have second order equations, we need two initial conditions. So, when we write the initial conditions like this at t is equal to 0, and similarly we also have to impose this initial condition as far as the Kelvin model is concerned, and when we try and solve it here, this is the expression that we are going to get. I have not made a mention of how this has to be solved, and if you look into the reference chapter that I have mentioned in the book Finlay, Lai and Van Ran, you will be able to see the detailed derivation. But as of now for this course, it suffices to say that this is the creep expression that we have got here. And in fact, you can do the following. If you look at it very carefully, closely, this is the creep of the Maxwell model, and what you see here is the creep of the Kelvin model. One should also note that this same Burger's model could be combined in different manners. It is not necessary that one should combine these get the same response. In fact, you can have different types of springs and dashpot combinations that can result in equations of this form, except that the material parameters that you are going to see here may be slightly different. So, you can generate different types of generalized Burger's models, which will have second time derivative of stress and strain, first time derivative of stress and strain as well as the stress, but the parameters will be slightly different. So, to summarize, the creep of Burger's model is the creep of Maxwell as well as the creep of Kelvin model. What do we really do with this kind of models? And this is at this point of time, we should just kind of take a small pass and find out what exactly is this exercise that we are trying to do here. So, when we started this lecture on linear viscoelastic model, we wrote down few important points that every viscoelastic model should show. The first and foremost thing is we should have an instantaneous elastic response, a delayed recovery, delayed creep as well as an instantaneous recovery as well as a delayed recovery, and you can have a permanent set or irrecoverable deformation, and similarly stress relaxation under constant strain. So, these are the essential features that we expected a viscoelastic model to have, and since we see such kind of response from real life material. So, obviously, whenever we sit down and work out some model, in a sense it should reflect the true mechanical response of the material. Now, looks like we have finally stumbled upon a model that could more or less follow whatever we were expecting from a linear viscoelastic model. But then the main problem here is how do we really determine this material parameters? We now have 4 material parameters to be determined, right. So, only if we have this determine this material parameters, we will be in a position to even use this model for any simulation model stress analysis if you really want to do. There are many ways of determining the material parameters. These days, if you are familiar with MATLAB, in fact, you will be doing some exercises on experimental data with MATLAB. So, you will be able to notice that one can actually find out the response, the material parameters by writing it within the constraint of optimization. But as of now, with the experimental data that we have got, it will be easy for us to make some guesses about the nature of the response of this material as well as the associated parameters. So, first and foremost thing what we can do is, we can actually take a look at how do we really find out some of these material parameters. So, the first parameter which is quite obvious to us is OA is equal to sigma naught by R1. So, that means if we have an experimental data of this particular form, and if you know that this is the stress to which it has been subjected to, by just looking at this particular loading as well as the recovery, we should be in a position to find out what is R1. So, that is the easiest parameter to find. Now, initially when I started discussing the model, I showed this spring and dashpot arrangement, and then I also mentioned that this model should behave like a fluid. So, if this behaves like a fluid, in fact you should verify whether it behaves like a fluid, you are basically going to see that it is going to asymptotically reach, if we keep loading this forever, it is going to reach a constant strain rate. When it will reach the constant strain rate, we actually do not know, because it will reach it only asymptotically. So, what we can actually do is, we can take the creep rate of the previous equation, which is equation 32, and this is what you are going to get, and at t is equal to 0, or what is given here as 0 plus, we are, when we substitute for it, we can measure that there is going to be some angle tan alpha, and similarly at t is equal to infinity, we are going to get something called as the tan beta, and we will be able to see that when we have, if we can measure this angle alpha as well as if we can measure this angle beta, and looking at the parameters that are associated with it, we can actually find out what is eta 1, we can also find out what is eta 2, and once we have analyze this experimental data like this, we should be in a position to find out all the material parameters. Normally, this is an kind of a thumb rule that is given for finding out the experimental parameters, but one can use these ideas to put some kind of a constraint for R1, what could be the values for R1, R2 as well as eta 1 and eta 2. And you will also notice here that you can verify what is the choice of eta 1 by looking at this particular value here, which more or less mentioned either as permanent set, and you are going to see that this particular value is independent of the running time. So, you are going to have this expression sigma naught T1 divided by eta 1. T1 is the time duration for which the material is subjected to a load of sigma naught. So, even by looking at the available deformation after sufficiently longer time, we will be in a position to verify whether this eta 1 that we got using this analysis that was mentioned here, okay, whether it is verifiable or not. So, these are one simple way of trying to determine the material parameters. There are many ways in which these material parameters can be determined. So, now how do we do the recovery? Since this is a viscoelastic, linear viscoelastic model, we are going to appeal to superposition. So, when I say superposition, what we are going to do is at T is equal to T1, I am going to add a constant stress of minus sigma naught, and so what will really happen if you actually look at the expression, you have sigma naught by R1, sigma naught by eta 1 times T, and this is the strain due to the Kelvin element, and then minus sigma naught by R1, sigma naught by eta 1, and this time now is now T minus T1, because T is the running time, T1 is the time up to which sigma naught is applied, and in the same way we keep substituting, instead of T we substitute T minus T1, and when we simplify the whole thing, you are going to see that this is the expression. The interesting point that you have to notice here is this first term, which is actually independent of the running time. So, that means this is going to be the amount of deformation that is what you will call really as permanent set. So, this is the expression that you are going to get for creep and recovery, but what do we do for stress relaxation? So, one can do the same thing, in the sense you have to solve the expression, constitutive expression that was shown here and do it. It will involve little bit use of Laplace transforms. So, if you are familiar with Laplace transforms, you can do it. If not, you can actually take the expression that is available in the textbook for solving it. Since the focus of this particular series of lectures is more on the mechanical characterization of bituminous mixtures, we won't get into the details related to the how to do the Laplace transform and how do we really get it, right. But if you see the particular chapter, you will see the analogous derivations here. So, what you now see here is a very general framework that we established here. We identified a spring for elastic element, a dashpot for a viscous element, and then we combined them in series, giving rise to a Maxwell model, in parallel giving rise to a Kelvin model, and then we realized that these two models cannot completely predict the response of a viscoelastic material. So, we put the Maxwell and the Kelvin model together in series to come out with yet another model, Burger's model, and it seemed to be doing most of the things. But is this an only unique model that is available? No, you can actually have different kinds of combinations of the model. So, you can have what are really called as standard linear solid. So, as the name suggests, the response of the material is like a solid material. In fact, I will just focus the attention only on this. You will see that this is a Kelvin model with a spring that is attached in series to it. You can actually have a standard linear fluid model, and you will see that it is the same Kelvin model with a dashpot that is attached in series, and you can have these kind of models, and incidentally you will see that the response of all these models that you see here will be identical, except that the parameters that are associated with the sigma dot, sigma double dot can be slightly different. For instance, you can get the same Burger's model by having two Maxwell models as you see here in parallel. Now, it is also time for us to take stock of the situation, because we introduced two types of time. One is a relaxation time and another is a retardation time. So, considering the response of the Burger's fluid model, wherein you have R1, R2, eta 1, eta 2, you can actually have two relaxation times for this material, for this particular model. Okay. So, Burger's model, you can have two relaxation time. Now, this is very interesting in the following sense. This model will come in very handy when you are trying to model the response of bituminous mixtures. Why? You can assume that your bituminous mixture consists of aggregate matrix plus asphalt mastic. So, you can prescribe one relaxation time to the asphalt mastic, another relaxation time to the aggregate matrix. So, aggregate matrix, you are talking about all the aggregate skeleton connected in the joints with the binder. So, you can assume that it will have one relaxation time, you can have the asphalt mastics in another relaxation time. You can also use this model for binder, because you can actually have asphalt in one relaxation time, malt in another relaxation time, at least. It can be used even for modified binders. You can have the polymer phase one relaxation time and the bituminous phase the other relaxation time. So, what we now understand is, if we have to explain the behavior of bituminous binders or bituminous mixtures, we at least need to have a model that will can exhibit at least 2 relaxation time, and that is more or less this the success of the Burger's model. So, in fact, it is not necessary that 2 relaxation time is good enough. We can actually have many relaxation time, and so that is why what we do is we go for such as generalized Maxwell models in series. So, that means you can have many Maxwell models having different values for springs and dashpot connected in series, and so the expression more or less will be of this particular type. And similarly, you can have what is really called as the generalized Vogt-Kelvin models in series, and again it can have as many relaxation or as many retardation times as you really want. And what we have seen in most of our modeling attempts, in fact, when we work with many of our students doing their PhD, sometimes we have even tried to use sets of more than 10 parameters at least to explain the response of bituminous mixtures over a range of frequency from 0.01 hertz to 25 hertz. So, this is the most interesting thing about this material. At different frequencies, the response of the material will be completely different, and so having a model which just has 2 relaxation time may not necessarily be sufficient. So, we need different relaxation, and in fact, these are normally prescribed in the following way in polymer literature. We call it as relaxation spectra. Okay, right. So, you can also have the generalized Maxwell model in parallel, and you need to have what is really called as the, to solve such kind of problems, you need to have what is really called as the differential operator algebra. I am mentioning all these things in passing because we are still working with linear viscoelasticity. We are not even talking about non-linear viscoelasticity, and in linear viscoelasticity itself, when we want to describe the response of bituminous mixtures and when we really need more than 4 or 5 relaxation times, the algebra that we need to do to solve a simple problem of stress relaxation or creep and recovery or in oscillatory mode can be really involved. So, we need to be aware of that particular part. So, let us summarize whatever we discussed in this particular series. So, we discussed Maxwell model, we wrote the constitutive expressions for the Maxwell model, and we showed that it will do a very good job of explaining relaxation, but when it comes to creep and recovery, whatever we prescribed about what a viscoelastic model should exhibit, it will not do a good job. Then we discussed about Vogt-Kelvin model, and we found out that it can do a decent job as far as the creep and recovery, because you still will not have a initial jump. So, I would, if I put a double tick here, I will put a single tick here for this, but when it comes to relaxation, this model cannot do any relaxation because you have a dashpot in parallel with a spring. So, it will not do anything. A Burger's fluid model can do creep and recovery, stress relaxation in a much better way. Of course, we did not show the expression for stress relaxation here, but it is understood that based on the structure of this model that we have got, we can have it. We also talked in terms of generalized models, especially when we want a range of retardation or relaxation time. Okay. So, this is the summary that I wanted to say here. This will more or less help us later to try and see how one can use the response of this material to describe different kind of scenarios. Thank you.